On February 14th, 1863, an astronomer basically squinted through this brass and glass telescope into a freezing winter sky, and, he found this peaceful, glowing smudge in the constellation Perseus.
Right, a very romantic Valentine's Day discovery.
But he had, absolutely no idea he was actually documenting a 147-million-year-old crime scene.
A violently active crime scene at that. I mean, we are looking at an object that is fundamentally tearing itself and its closest neighbor apart.
Wow. Well, welcome to the deep dive. Today, we're taking a look at a really dense, data-rich Wikipedia entry about a specific spiral galaxy. It's known as NGC 1268.
Right.
And we're going to extract the hidden physics and just the sheer drama inside those numbers. Because our mission today is to decode this complex astronomical data for you.
Yeah, exactly. Bypassing the dry tables to really understand what a single galaxy's profile tells us about the dynamic, fluid nature of our cosmic neighborhood.
Right, because it's so easy to just look at a source text filled with, coordinates, classification codes, decimal points. Just let your eyes glaze over.
Oh, absolutely. But our goal here is to translate that rigid data into a three-dimensional living picture of the universe. Because every single metric on this page is a clue to how this galaxy functions, how it was born and how it might eventually die.
Okay, let's unpack this.
Yeah.
To understand the crime scene, we really need to look at the victim's profile first.
Okay, sure.
So the source classifies NGC 1268 as an intermediate spiral galaxy, right, located in the constellation Perseus.
Right, the Perseus constellation.
But then it gives this highly specific morphological classification that says it's an SAB parentheses RS parentheses lowercase bb, which, I know the S stands for spiral, but that string of letters just feels like a router password.
It really does.
What structural anatomy does SEB RSB actually describe?
Well, it's actually an incredibly precise map of the galaxy's skeleton.
Oh, really?
Yeah, so the SAB part means it's an intermediate spiral. It has a central bar of stars cutting across its core, but that bar isn't quite as pronounced or rigidly defined as the one in, say, our own Milky Way.
Okay, got it.
Then you have the R's in parentheses. That indicates an inner ring structure. So gas and stars are congregating in this loose ring just outside that central bar.
Oh, fascinating.
And finally, that lowercase b tells us about the spiral arms themselves. They aren't tightly wound around the core like a spool of thread, but they're not completely loose and fragmented either. They're, moderately wound.
Okay, so we're picturing a central glowing core, a faint, straight bar of stars across the middle, a glowing ring around that, and then sweeping arms kind of trailing off into the dark.
Precisely. And it's doing all of this on a massive scale. The data puts its size at roughly 55,400 light years across.
Which is smaller than our Milky Way, but we're still talking about a structure containing billions of stars.
Oh, easily.
And yet the source notes its apparent size from Earth is tiny, like just 1.0 by 0.6 arc minutes. So if you're looking up at the night sky, you are absolutely not seeing this with the naked eye.
Not a chance. An arc minute is a 60th of a degree. To put that in perspective, the full moon is about 30 arc minutes across. So NGC 1268 is a fraction of the size of the moon in our sky.
Wow.
It's incredibly faint and incredibly small from our vantage point, which, makes sense given the distance listed here. It's 147.3 million light years from Earth.
Yeah, and I noticed the data includes an error margin there, plus or minus 10.3 million light years.
Yeah, which really highlights the extreme difficulty of measuring cosmic distances. When an object is that far away, our standard geometric tools like measuring parallax as the Earth moves around the sun, they completely break down.
They just don't work anymore.
Exactly. We have to rely on the behavior of light itself to gauge the distance, which is what introduces that margin of error.
Right. Now, looking at the data, it pins its right ascension down to, 3 hours, 18 minutes, 1985 seconds.
Very specific.
Yeah, and the declination is plus 41 degrees, 29 minutes, 19 point something seconds. We don't need to read out the raw GPS coordinates to understand why that precision matters, though.
Yeah.
You need those exact coordinates because of how many different teams are constantly looking at this exact spot.
Exactly.
And that actually brings up something that stood out to me in the source. The sheer number of catalog names.
Ah, yes. The alphabet soup of astronomical designations.
Right. It's primarily known as NGC 1268 for the New General Catalog. But the data lists all these other alternate identities. There's UGC 2658, MCG plus 0707056, PGC 12332.
CGCG 54093.
Yes. All of those. And my initial thought was that this is like a person having, a driver's license for the DMV, a passport for travel, and a social security number for the IRS.
Yeah.
But it's more than just administrative paperwork, isn't it?
It is, yeah.
Because these different acronyms represent fundamentally different ways of seeing the galaxy, right?
They absolutely do. That's a vital distinction. When you see a list of catalog names like that, you aren't just seeing different filing cabinets, you're really seeing the history of human observation.
Well, that makes sense.
For instance, UGC is the Uppsala General Catalog, which focused on galaxies visible from the northern hemisphere above a certain size limit. But MCG is the Morphological Catalog of Galaxies, which was this massive Soviet project that meticulously classified the visual shapes of tens of thousands of galaxies based on photographic plates.
Okay, so it's more like a medical file.
Hmm.
The NGC name might be the basic photograph of the patient, but another catalog might be the X-ray showing the hot gas. And another might be the MRI showing the ancient cooler stars in the infrared spectrum.
That is a much better way to think about it, yeah.
Yeah.
Different sky surveys are conducted by different teams using varying wavelengths of light to achieve completely different scientific goals.
Right.
If a team maps the sky looking specifically for radio emissions from active galactic nuclei, they generate a new catalog. If your galaxy emits those radio waves, it gets a new ID tag. So having 5 or 6 different catalog designations tells you that NGC 1268 is an object of sustained multidisciplinary scientific interest.
Right, but all those different catalogs are basically taking snapshots of a moving target. And when I say moving, the data here is just staggering.
It really is.
The source lists its heliocentric radial velocity at 3,222 kilometers per second, with an incredibly tight error margin of just plus or minus 2 kilometers per second.
Yep.
And it also lists its redshift at 0.010748.
Right, and those two numbers are inextricably linked.
Well, I know that redshift indicates an object is moving away from us, right? The light waves are literally being stretched out toward the red end of the spectrum because the universe is expanding.
Exactly.
But 3,222 kilometers a second, is that speed entirely due to the background expansion of the universe?
Yeah.
Like the Hubble flow?
Wow.
Or does a specific redshift of 0.010748 suggest something else is pulling on it?
That is exactly the right question to ask. At a distance of 147 million light years, the expansion of the universe certainly accounts for a large portion of that extreme velocity. As space itself stretches, the galaxy is carried away from us.
Right.
But the precision of that measurement, plus or minus just 2 kilometers per second, allows astronomers to isolate its peculiar velocity.
Peculiar velocity.
Yeah, that is the galaxy's actual physical motion through its local environment, independent of cosmic expansion.
Oh, wow. Which means it's falling towards something.
It is barreling through space. And moving at 3,200 kilometers a second has severe consequences. You cannot tear through a neighborhood at that speed without interacting with your environment.
Yeah, I'd imagine not.
And that leads us to the critical context provided by the source. NGC 1268 is a member of the Perseus cluster.
Now, anyone following astronomy knows that a galaxy cluster is a massive gravitationally bound system. But the Perseus cluster is particularly notorious, isn't it?
Oh, very much so.
Like, it is one of the most massive objects in the known universe, filled with thousands of galaxies surrounded by a vast cloud of multi-million-degree X-ray gas.
It is an incredibly dense, chaotic, and high-friction environment. Being a member of the Perseus cluster means NGC 1268 is constantly navigating a treacherous gravitational landscape.
Just dodging traffic constantly.
Pretty much. And the source specifically notes the visible damage of that navigation. It states that NGC 1268 appears to show signs of distortion in the form of bridges, and that these features are likely the result of a strong interaction with a neighboring galaxy, NGC 1267.
Okay, so when the source says bridges, it's easy to picture a rigid structure.
Yeah.
A literal suspension bridge connecting two cosmic islands. But gravity doesn't build suspension bridges out of stars.
No, it doesn't.
How does a stream of stellar material physically hold together across the vacuum of space?
Yeah.
Like, is this more like pulling apart warm taffy? Are these two galaxies actually ripping stars from each other's outer edges?
What's fascinating here is that the taffy analogy is spot on. They are absolutely doing that. And it all comes down to differential gravitational pull, or tidal forces.
Like the moon pulling on Earth's oceans to create high and low tides.
Exactly like that, but scaled up to billions of solar masses. As NGC 1268 and NGC 1267 pass close to each other, the gravitational field of 1267 pulls on the near side of 1268 much more strongly than it pulls on the far side.
Because gravity weakens with distance. So the side facing the neighbor feels a much more violent tug.
Correct. And that differential pull overcomes the internal gravity holding the galaxy's spiral arms together. Stars, gas, and dust are literally sheared off the outer edges.
Wow.
They get drawn out into a long, trailing filament, a tidal tail or a bridge.
But wait, if the gravity is pulling that hard, why don't the two galaxies just immediately collapse into each other? Like, why does it form a bridge instead of just a single instant car crash?
Because of angular momentum, they aren't just falling straight toward each other, they're orbiting the center of the Perseus cluster, moving at incredible velocities.
Oh, I see.
So they're sliding past one another. The bridge is a visual record of their orbital dance. The material gets stretched out in the space between them as they swing by.
It's essentially a slow-motion fluid dynamics experiment playing out over millions of years.
Exactly.
The distortion, the pulling, the stretching it fundamentally alters the morphological classification we talked about earlier.
Yeah.
That SEBR's B shape is being warped in real time.
And this is why it is so important to look past just the static numbers on a Wikipedia page. Galaxies are not static paintings. They are fluid, they're malleable.
Yeah.
This interaction forces massive clouds of cold gas to collide, compressing them and triggering intense waves of new star formation. A violent interaction like this both destroys the existing structure of the galaxy and seeds the birth of millions of new stars.
So it's a slow-motion collision course where the debris is made of glowing plasma.
Beautifully put, yeah.
But that slow-motion environment, the millions of years it takes to form a tidal bridge, that sets the stage for an event in the source data that is incredibly fast. Like sudden, violent, and rapid.
The flash of 2008.
Right. The data notes that a supernova was observed inside NGC 1268. It was named SN 2008, and it was discovered on August 30th, 2008, by the Lick Observatory Supernova Search, or LSSS.
This completely shifts our timeline from millions of years to a matter of days.
Yeah, and the numbers provided here require a bit of unpacking, I think.
Oh, for sure.
Here's where it gets really interesting. The source lists the overall apparent magnitude of the host galaxy, NGC 1268, as 14.2, but it lists the magnitude of the supernova itself as 18.8.
Right.
Now, in normal terms, higher numbers sound bigger and brighter. Wait, so the galaxy has a magnitude of 14.2, but the supernova was 18.8. Is an 18.8 magnitude explosion just blindingly bright?
It's actually the exact opposite. I know it's counterintuitive, but the astronomical magnitude scale is backward.
Oh, really?
Yeah, it originated from ancient astronomers who ranked stars from first class down to sixth class. So a smaller number is brighter and a larger number is dimmer. So an 18.8 is incredibly dim. Substantially dim. To give you a sense of scale, the faintest objects you can see with the naked eye in a pitch black sky are around magnitude 6.
Okay.
The galaxy itself, at 14.2, requires a serious telescope to capture, and the supernova is an 18.8. Because the magnitude scale is logarithmic, that means the supernova was roughly 70 times fainter than the combined light of the galaxy it sits inside.
Wow. Okay, so my question is, how on earth do you spot an 18.8 magnitude pinprick of light against the glowing, distorted backdrop of a 14.2 magnitude galaxy core? How does the LS team actually find that?
They use a technique called digital image subtraction, and it relies entirely on automated telescopes and algorithms.
Oh, so computers are doing the heavy lifting.
Exactly. The Lick Observatory Supernova Search utilizes a robotic telescope that photographs thousands of galaxies every single night. The computer takes a new image of NGC 1268, lines it up pixel by pixel with an older reference image of the exact same galaxy, and literally subtracts the light of the old image from the new one.
So if nothing has changed, the result is just a completely blank black image.
Yes. The blinding light of the galaxy's core is mathematically erased. But if a single star has exploded and brightened in the intervening days, that one pixel won't cancel out.
It'll just pop up.
Right, it'll leave a tiny, faint dot on the subtracted image. That is how you catch an 18.8 magnitude blink 147 million light years away.
That is an unbelievable feat of engineering. And it matters immensely because the source explicitly classifies SN 2008 BRAM as a Type Ia supernova. And in astronomy, finding a Type Ia is like striking gold, isn't it?
Oh, it's the holy grail of cosmological distance measurement. Type Ia supernovae are what we call standard candles.
Right. But how do we know they're standard? I mean, the universe is incredibly chaotic, as we've just established with the Perseus cluster. How can we be sure that every Type Ia supernova explodes with the exact same underlying physics?
Because of a very rigid physical threshold known as the Chandrasekhar limit.
The Chandrasekhar limit.
Yeah. A Type Ia doesn't happen to a massive star collapsing under its own weight. It happens in a binary system, where a dense, dead white dwarf star orbits a companion. The white dwarf acts like a parasite, using its intense gravity to slowly siphon gas off the companion star.
Oh, so it's stealing mass.
Exactly. And it keeps stealing mass until it hits a very specific mathematical tipping point, which is 1.44 times the mass of our sun.
Okay, 1.44.
The instant it crosses that threshold, the white dwarf can no longer support its own weight. It collapses and detonates in a runaway thermonuclear explosion. Because that trigger point, 1.44 solar masses, is a fundamental law of physics, the resulting explosion always produces roughly the same peak absolute luminosity.
I see. It's like knowing exactly how loud a specific standardized model of a firecracker is. If you know its true volume and you hear it go off in the distance as barely a whisper, you can use the dampening of the sound to calculate exactly how many miles away it detonated.
That is a perfect analogy, yeah. By measuring the incredibly faint 18.8 apparent magnitude of SN 2008 Fran and comparing it to the known true brightness of a Type Ia explosion, astronomers can independently calculate the distance to NGC 1268. It is a critical mathematical check that verifies that plus or minus 10.3 million light-year distance we discussed at the start. Finding a standard candle inside this galaxy calibrates our entire understanding of its place in the Perseus cluster.
That's incredible. And that standard candle really serves as a pivot point for the human timeline of discovery embedded in this data, right? We have this ultra-modern 2008 discovery facilitated by robotic telescopes, algorithmic image subtraction, and advanced astrophysics regarding the Chandrasekhar limit.
Right, very cutting edge.
But the source grounds this modern science by looking back to how our view of this galaxy began. Go back to Heinrich de Rest, February 14th, 1863.
Squinting through a 19th century optical telescope in the freezing cold.
Right. He had no computers, no image subtraction. He was just a human eye behind glass lenses, sketching a smudge by hand. And contrast that with another detail in the source. It provides an image of NGC 1268 taken recently by the Euclid Space Telescope.
Oh, Euclid is amazing.
An observatory literally parked in space, free from the blurring effects of Earth's atmosphere, utilizing massive digital sensors. It's like drawing a landscape from a blurry memory versus looking at a high-definition 4K photograph.
If we connect this to the bigger picture, it's about how science builds on itself.
Yeah.
I mean, de Rest didn't have the optics to see the gravitational bridges. He certainly couldn't see a Type Ia supernova.
Yeah.
But he did the most essential thing a scientist can do. He formally documented the position. He assigned the coordinates.
He laid the foundation so that 160 years later, the Euclid Space Telescope knew exactly where to point its cameras.
Exactly. And the Euclid mission isn't just taking pretty pictures. Its primary objective is to map the geometry of the dark universe, to understand dark matter and dark energy. And how does it do that? By looking at the exact kind of structural distortion happening to NGC 1268.
Oh, because dark matter exerts gravity. So
Yeah.
to map dark matter, you have to look for galaxies that are being gravitationally sheared and stretched.
Precisely. The tidal bridges connecting 1268 and 1267, the warping of that SAB-ERS-B spiral structure, that morphological damage is a direct tracer of the unseen gravitational fields in the Perseus cluster.
That is so cool.
Yeah, by analyzing the high-resolution images from Euclid, astrophysicists can reverse engineer the distribution of dark matter that is causing the taffy pull effect. De Rest's faint visual smudge has become a crucial data point in understanding the fundamental architecture of the universe.
So what does this all mean for you? When you look at a Wikipedia page full of raw astronomical data, right, ascension, declination, radial velocity, morphological classifications, it's super easy to just scroll past it and dismiss it as bookkeeping for nerds.
Oh, definitely.
But hidden inside those dry columns is a violently dramatic narrative. It is the story of a galaxy plunging through the high-friction environment of the Perseus cluster at over 3,000 kilometers a second.
Yeah.
It's a story of tidal forces, literally ripping streams of stars out into the vacuum of space like warm taffy. It's the story of parasitic white dwarf stars detonating with enough thermonuclear force to serve as cosmic firecrackers, allowing automated algorithms on Earth to measure the scale of the universe.
It's a reminder that data is never just data. It is the blueprint of a fiercely dynamic reality.
Right. And speaking of that reality, there's one final lingering implication in all of this that I just can't shake. It comes directly from that distance constraint of 147 million light years.
The time delay. Because light has a universal speed limit. Looking out into the deep cosmos is literally looking backward in time.
Right. The light we are seeing from NGC 1268, the high-definition structural damage captured by the Euclid Space Telescope, the faint 18.8 magnitude blink of the supernova in 2008, the distorted bridges of stars sheared off by NGC 1267, None of that is happening right now.
Not even close.
Yeah.
That light took over 147 million years to cross the void and reach our telescope mirrors.
Which is mind-blowing.
It is, which means the violent interaction we are so carefully observing actually occurred during the late Jurassic period here on Earth.
Wait, really?
Yes. While stegosauruses were walking around, the photons carrying the image of that supernova began their journey.
That is deeply unsettling to think about.
So I want you to consider this the next time you look up at the night sky toward the constellation Perseus.
Yeah.
Given that NGC 1268 has a verified radial velocity of over 3,200 kilometers per second,
Yeah?
and given that it is locked in a violent, destructive, high-friction collision course with its neighbor, what does NGC 1268 actually look like right this very second?
It's entirely possible the tidal bridges have been completely severed. The two distinct galaxies could have finished their orbital dance and merged into a single, massive, unrecognizable elliptical structure. The spiral arms, the central bar, the inner ring we classified so precisely, they could all be completely gone.
The physics dictate that it has almost certainly undergone a radical transformation. The data profile we've been decoding today is effectively a historical document.
Right.
We are studying the ghost of a collision, and it is a mystery we won't know the actual present-day answer to for another 147 million years.
147 million-year-old ghost of a collision. It really recontextualizes that opening thought, doesn't it?
It really does.
When Heinrich Duress peered through his eyepiece in 1863, he thought he was finding a peaceful patch of light in a calm, clockwork universe. He had no way of knowing he was staring at a chaotic brawl hidden behind neat and tidy coordinates. So the next time you expect things to be clean, static, and easily categorized, remember the violent, ever-changing reality of NGC 1268.